All right, let's see. Hello everyone, it's December the 27th. I think I'm pushing the laptop to kind of extreme. I'm running a tuning, hyperparameter tuning right now, which has been running for 30 minutes. I suspect it's gonna be running for at least maybe an hour. So I'm just like, nah, might as well take this opportunity to do this. But it's like live streaming and hyperparameter tuning at the same time. I don't know. We'll see if it still works. So I'm gonna open this web page and see how long it's gonna take. Oh wow, I am very impressed. I thought it's gonna be significantly impact. I'm looking at the speed of the live stream. It looks very stable. Everything seems to be as if the tuning is not happening, but if you take a look at my activity monitor, you can look at this. Look at this. This is the CPU currently, right? It's 100%. And I have, 10 of these running. So I'm very impressed. But the speed might have something to do with the memory. The memory is still low. It's it's not really that heavy on the memory side. But wow, with that heavy CPU, it's still working pretty well. I'm impressed. I'm seriously impressed. All right, anyway, let's do this. Remove stones to minimize the total, okay? Given a zero index integer array, piles, where piles I represent the number. Oh, before I do this, I gave this problem a little bit more thought last night, and I think I have a solution. I'll deal with this later, right? But the solution is, I think, is binary search. Yeah, we'll get to this. Okay, where am I? I have piles, and each one represents the number of stones in the pile, and an integer k. I should apply the following operation exactly k times. Choose any piles I, and then remove floor piles I. So just integer division stones from it. Notice that you can apply the operation on the same pile more than once. Return the minimum possible total numbers of stones remaining after applying the k operations. So basically every time we want to remove the highest, right? Because we want to return the minimum possible total number of stones remaining, which means each time when we do the division, we want to divide the largest number. And when we do the division, I'm thinking about if even or odd has anything to do with this. Even and odd. I mean, when we divide by 2, it doesn't really matter. It's reduced to the same value if it's even or if it's odd. Yeah, like 8 divided by 2 is 4. 9 divided by 2 is also 4. So it doesn't really matter. So this becomes very clear. We're going to turn piles into a heap, into a main heap. So we can always pop out the biggest value, and then we divide it by 2, push it back, and then pop out. We do it at k times, and then we return the sum. Yep. That will be my solution for this one. Wow, this is not a terribly difficult one. Does it count as greedy? Oh, you might count. Oh, like this is actually kind of slow. I was trying to open this and then it took a while. Hold on, why did you open it there? I have something open here. All right, I don't need this. I don't need this. I don't need this. Nor do I need this. I should just focus on these. So what do we have? We need a heap. Now we'll just import heap. Heap q. Okay. And heap shall equal to minus p for p in piles. And heap q dot heapify heap. Then for this in range k might be That should be fine. We just do k times. It's okay. You can do a k time. Even if things become 0, it's okay. So we just do k times. For each time, we say heap q.heap pop. Right? We'll pop the heap. After we pop, we'll take the minus. Right? And then we'll divide it by 2. And then heap q.heap push. Heap. So we push it back. Ooh, no, we don't have to do this. We'll just push it back as it is. We push it back, we do it this time, and then we return some heap, but we take the negative of it. Alright, let's not be too cocky. Let's just go through our old format just to make sure that everything is exactly how we would like it to be. Oh, but I just realized I want to see the negative value when we do divide. It's kind of tricky, so I'd rather take the negative and then put a negative on the outside. I have been bitten by this more than once, just to be on the cautious side, because negative division is always tricky. Like, it doesn't give you the one that you're actually expecting. Sometimes. And this doesn't really cost too much, so it's okay. We don't want any weird error. Okay, piles and K. Try it. And it's now correct. Ooh, that. See? I said don't be too cocky. That was interesting. I got a 10. How? I just divide by... Oh, shoot, floor. Wait, hold on. No. Divide by 2 is 4.5. We do floor is the greatest integer that is smaller or equal to x. How'd you go to 5? Nine divided by 2 is 4.5. Huh? This is ceiling. This is ceiling. Wait. Come on. You serious? $12 and $12. That is ceiling. That is not floor. Right? 5 divided by 2. It gives you 3. That's ceiling. Dude. Let's see this one. 6. 7 divided. Yeah, this is 4. Oh, man. That. Ceiling. You see that? That's now floor. I don't think that is right. Oh. That is not right. Come on, people, make some. Nobody talk about the ceiling or stuff? Yeah. Oh, shoot. I think my understand. Oh, minus. Oh. Okay, my bad. You did put the remaining in. Oh. Okay. Okay. It was my bad. I was like ceiling floor. No, that's the amount taken away. Okay, that's the amount taken away. So if we're taken away is the floor, then the remaining is this is actually not right. This is not according to let's redo this. Okay, yeah, this is not right. Okay, so we can say p equal to minus heap q dot heap pop, right? And then we shall put in p minus p divided by 2. There we go. That's the right one. That's the right one. That's the right one. I was wrong. Alright, I was confused earlier. We remove the floor number of stones, which means the remaining number of stones is the ceiling, right, of each pile divided by 2. But it'd be better if we implement it according to the definition. And log n. Right? Yeah, let's do this. I don't know why. Maybe the ceiling? I don't think so. No, it may be. Divided by 2 might be faster than calling the ceiling and the floor. Okay, so are we done with this? Alright. Binary search. Binary search. So, okay, here's the epiphany that I have last night. So it doesn't matter, right? We have the count and then we have the divisors. So the best strategy we can have is to have the first, n values to fill as much as possible. So we can find we can just take out, okay? We take out all the values that cannot be used. Okay, because it's definitely the multiples of divisor 1, multiples of divisor 2, these cannot be used. And the remaining values can all be used. Okay, so if we set a higher bound, we don't know what the higher bound is, we can just set a higher bound. And the higher bounds actually can be however high you want, doesn't really matter. You set up a higher bound, right? And then we say within this bound, like that range, how many values cannot be taken, then the remaining can all be taken, right? So we have multiple of divisor 1 plus multiple of divisor 2 minus the multiple of both divisor 1 and divisor 2. And that will be the total number you cannot take. Then you have the total bound, you have the number you cannot take, then the remaining values are the number you can take, right? And then we compare that value to unique count 1 plus unique count 2. If it's too big, too many counts, then we shift it left, right? We move it to the left. Otherwise, we move to the right. And then eventually we'll hit the value. Okay, so now the question is, I have the total number of counts, that's just divided by this. And that's just divided by this, right? And then we want to find a value, which is the least common multiplier of these. So it will be just divisor 1 multiplied by divisor 2 divided by their GCD. So we have to do that, and then we will be able to get something. Yeah, this is analysis, right? We try to analyze it. It's not gonna work. Okay, so we'll have LCM, right? Will be divisor 1 multiplied by divisor 2 divided by GCD, divisor 1 and divisor 2. Okay, so we can have low and high. Low will be we call it 1. All right, guys, we start with positive integer. And high, that is a interesting problem, because I was thinking high can just be, you know, unique count 1 plus unique count 2. That's actually correct, unique count 1 plus unique count 2. Because it's not going to be larger than this. And just unique count, oh, come on, unique count 1 plus unique count 2. That is higher bound, right? And while low is smaller than high, and we have to analyze because it's at the minimum, so what we want to do is, yeah, let's do this first. Low plus high divided by 2, right? And then we shall say, given this, what are the values we can remove, or no, the values we can take. So can take shall equal to mid minus the value we cannot take. That will be mid divided by divisor 1. Okay, these are the values that's divisible. Plus mid divided by divisor 2. These are values divisible by the second one. And minus the, because we have the LCM gets counted twice. So we minus that. So that will be the total can take, right? When we say if can take is larger than, okay, that this is, if it's larger than, is we want to move up, all right? So if we say if it's larger than what? Oh, I didn't think this through. It's larger than what? We have the total count of 1, right? The total count is 2. And it should be unique count 1 plus unique count 2. Hold on. Doesn't feel right. Yeah, we have a total is this. So we take those away, and the remaining shall be the count. Then this is not right. The high cannot be this plus this, right? The high must be this plus this and a little bit more. Look at this. Plus together is, I honestly don't know. I mean, what will be the kind of worst case scenario? I don't know. We have that many, so like twice, like 2. Like 2 would be the worst. Yeah, I think the worst case is both divisors are 2. So that's the worst case, right? That's the worst case, because if this is 2, so we can take a 1, 3, 5 all the way to here, right? And then if the second divisor is 2, we cannot take any of this, so we have to do it all over again. So it's just this plus this times 2, and that's the worst case scenario. 2 times this, I might as well plus 1, right? So now we can say if it's larger than unique 1 plus unique 2, right? If it's too big, then we say high, right? Well, equal to mid. Else we say low equals mid plus 1. Let's see if this makes sense. So if the total number we can take is too much, right, which means the mid we set as too high, so we want to set the high into the mid, right? High into the mid. So if it's too much, we always go divide by 2, divide by 2, divide by 2, right? And eventually, because mid is, it will stay with this. So it will be low plus 1, then they will be equal, right? Low plus 1, which means if they're equal, if it's large, if it's too large, we do this, and eventually coming out, it will be mid plus 1 when it come out, which means its can take is smaller or equal to, right? Smaller or equal to this. And then we go up. Okay, we guarantee it's going to be equal to then. If can take is smaller, then it will be this plus 1, right? Because this plus 1 will cause it to come out. So if it's smaller than the plus 1, it will be equal. But if it's equal, it will be too much. So we should change it, right? So say if can take is larger or equal to, then the high will be, so it will always be smaller. It's smaller, goes up. Then I think I will do it this way, okay? If I do it this way, I can just return low. Give this a shot. Oopsie doozy, what the hell? GCD is not mentioned. Of course it's not mentioned. It's math.gcd. No, it's not right. Okay. Don't worry. Yeah, let's analyze again. I feel I'm on the right track, but it's okay. That's okay. All right, so we are just I'm gonna observe, okay? I'm gonna observe each step, and we probably want to print mid and can take as well. Lord. Okay. We start with 1 and 9 because we have 1 and 4, 8, and 1 and 9. So the first one I say is 5. Okay. The first one I say the end is 5. Okay. Then we say 5 divided by 2 is 2. So we have 2 we cannot take. 5 divided by 7 is 0. So from 1 to 5, I only have 2 that I cannot take. Right? So if I have 2 and a 5, minus 2 is 3. That is not right. Hold up. 1, 2, 3, 4, 5. Right? So I cannot take 2. I cannot take... Oh, that's not right. I can take 2 for the other one. I was so confident, I was so confident that I was actually wrong. Okay. This is not right. This is not correct. So we have something I cannot take. But hold on. We know there are values we cannot take. The LCM cannot take. Okay? The LCM definitely neither can take. So the remaining value, right? Oh, yeah, this is not right. It ain't right. The remaining value I can have, so basically this is saying from 1, 2, 3, 4, right? 1, 2, 3, 4, 5, right? We do 1, 2, 3, 4, 5. 2, 4 cannot be taken by divisor 1. So 1, 3, 5. So we have 3 value that can be taken by either one. Okay? 3 value can be taken by either one. And then we have 2 value left, which cannot be taken by one, but can be taken by the other. So what we can say is I have certain number cannot be taken by divisor 1. Certain number cannot be taken by divisor 2, but can be taken by the others. And we have certain value cannot be taken by both, so these are eliminated. And we have the remaining as both can take, right? Both can take. So what we can do is saying, among the value that cannot be taken by just multiple of d2, right? There are multiple of d2, and since I take out the LCM, so they shall not be divisible by d1. So I can say if I want to fill d1, I'll take whatever is cannot be taken by d2 plus a chunk of this, and whatever, and a chunk of this, and try to see if it works. And okay, that might work. So basically cannot be taken by d2. I have a so basically the cannot be taken by d2 plus a chunk of both cannot be taken, right? And then cannot be taken by d1. Because that's savings, right? That is savings. Cannot be taken by d1, and then plus the remaining that we cannot be taken. And then we see, we're trying to see, what are we trying to see? If we say, we handle divisor 1, so cannot be taken by 2 plus something, right? Can be taken by both. All right, so this is what I need. And the remaining is the d1 and the remaining things, right? And if we have too many of this, right? If I have too many of this, then this will be a negative value. Then we do this. Then we say the can be taken here. So we just add these two together. So we take one, try the other one, see if it's larger than 0 or smaller than 0. If it's smaller than 0, it means not enough. If it's larger than 0, that means we can push it even harder. So now this is not correct. I agree. But we can do, okay? So we can say none d1 d2 shall equal to mid LCM. Okay. None d1 cannot be taken by d1 shall be mid divisor 1 minus none d1 d2. None d2 shall be the mid divided by divisor 2 minus none d1 d2. Okay, so both, right? Both can be taken as mid minus none d1 d2. Well, this cannot minus none d1, but it can be taken by d2, and minus none d2. Okay, so now we have this, right? We can say fill up d1 first, right? If I want to fill up d1 first, then what we need is none d2, so the things that cannot be fit in d2, right? So none d2, but I can use this for d1, and plus unique count this, right? Unique count. Oh. Check whether there is enough for d2. So basically we'll fill up, right? We'll fill up using that, right? And then what? And then, because those will be none d2, right? So yeah, so we say if none d2, we'll fill up d1 first, right? If none d2 is larger or equal to d1, no, larger or equal to unique count 1, then we can have both plus none d1, right? All of this can be suitable for D2. Capacity for D2 equals this. Else, then capacity D2 shall equal to none D1. Definitely, we can use all of them. And on a plus, because none D2 is smaller, then we can say unique count this minus none D2, right? Minus none D2. That's the number that we have to take from both. So both minus this, right? Both minus this, which means if this is larger than this, and this will be a negative value. So I can just say the maximum of this and 0. Then we cover both, because if this is too big, this will be negative, so it will be 0. So that's the capacity D2, right? That will be the capacity D2. And then we say fill up D2 first and check whether there is enough for D1. How we do that? So we say capacity D1 shall be none D2, right? So we do is enough for D1, so that's the D1 plus both minus maximum unique count 2 minus none D1 and a 0. Okay. Then we say if either one of them is, we say if capacity D2, right, is larger or equal to unique count D2, or capacity D1 is larger or equal to unique count 1. If any one of those is good, then we can say high equals mid. Else, which means both are smaller, right? Both are smaller. So in that case, I need to make it bigger, make the whole thing bigger. Okay, you want to give this a shot? Ooh, this one's right. That looks a little bit promising. Oh, okay, so we have this is wrong. Damn, I was so happy. All right. Man, this is oh. Yeah, it's a little, I don't know. I mean, well, maybe it will be better to really do a debugger. I'm just too lazy to use the debugger, and I actually don't remember a lot of the commands. Oh. Result is 13, answer is 15. Okay, doesn't matter. We can figure out ourselves, and then we'll just print capacity D2. Okay, and capacity D1. And then we'll do this. All right, let's do this. Okay, so what do we have? We have D1 is 2, D2 is 4. Ew. Count 1 is 8. Count 2 is 2. Right, it's this thing. It's this thing. Okay, so we have from 1 to 21 to choose. And the mid, I forgot to print the mid. Okay, the mid is 11. Okay, 11 is... Okay, 11. And none D1, D2 will be 4 and 8. That's correct. None D1. Well, D1 will be 2, 4, 6, 8, 10. All right. So for a non D1 is 3. Okay, so we have 3 is non D1, and then a capacity for 1 and a capacity for. So with this, non D1 D2 is 2. So can we get them both? Yeah, I want to have every single piece. So both capable is 6, right? So if we take a look, if we write it out, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So 4 and 8, these are just, they cannot do, right? And then none D1, we have 3 of them, so basically that's 2, 6, and 10. None D2 is nothing. So the ones that can have both is 1, 3, 5, 7, 9, 11. 1, 2, 3, 4, 5, 6. That is correct, right? So if I want to fill D1 first, and D1 is asking for how many? D1 is asking for 8. Okay, want to fill 8, then none D2 is 0. So we need to take all of them from both. And both we only have 6, right? I have 6 from both, and we need 8. So this will be a -2, right? So for 2 will be none D2 will be 3. So the capacity is 1. Now that's not gonna work. Actually, I kind of see the problem. Fill up D1 first, okay? Fill up D1 first. Capacity D1. Let's actually do this capacity D1, right? What's the capacity of D1? Well, the capacity of D1 is none D2 plus both, all right? And here capacity of D2 is none D1 plus both. So we say if it has to be both. If one of them is not possible, then we cannot do, right? Is possible, is good, scenario 1 shall be capacity of this shall be larger or equal to unique 1 and capacity 2 is larger or equal to unique 2. Okay, and then we do the same. This is good, and we can just say is good 1 is good 2, and then we say if is good 1 or is good 2, one of them is good, then we can continue, otherwise we don't. This one pass. Yeah, I think it's just we sometimes capacity 1 doesn't fulfill, but capacity 2 might be able to fulfill, and then we just let it pass. That's why it's not right. Okay, so we'll comment out and run all of them again. Look at this. Look at this. Now I have confidence. Let's do this. Let's throw this in. Throw this in. I think I pressed the wrong button. Okay, we can do. Holy crap. You wanna? Yeah. Let's do some. 72 minutes, still going. All right. What are we doing? From random. random import, randint. Okay. Now what? We want a divisor 1, divisor 2. Both have to be this. That's okay. We just say for this in range. Here's 50 test cases for this. I have confidence, but just, rand int. Okay, let's be very bold. 2 to 10 to the 5th. Okay, this is the first one. This is the second one. 2 to 10 to the 5th. Actually, don't do 10 to, I think to 100 will be good enough. Yeah, let's just do 100. And 1000. How about this? Rand int 1 to 1000. Last one, rand int 1 to 1000. Okay. Just throw this in and give me some. Give me some. Come on. That is correct. I have confidence now. I think I'm gonna submit it. Okay. You want a edge case? Yes, I do want edge case. 2, 2. 2, 2, 2, 2. How about this? This kind of edge case. Or maybe 1, 1. 1 and 1. Take the smallest possible. Yep. Let's go. Come on. Come on. That's it. That's it. Good problem. Good problem. So I was right, but I was wrong at the same time. So I was correct, right? I was correct that the idea should be binary search, but the initial implementation was not correct. Yeah. Now the current implementation breaks down the number of values that we can take from 1 to mid, right? From 1 to mid, we break it down from 1 to mid into 4 categories. Okay, category 1 cannot be taken by either D1 or D2. Category 2 can be taken by D1 but not by D2. 3 can be taken by D2 but not by D1. And 4 can be taken by both. Right? Now these counts can be computed by using division and LCM of D1 and D2. Now to maximize, right? To maximize the use of the availables, right? We want all the values, right? We want all the values not divisible by D1 come from, yeah, we can call it none D1 D2, right? This one will be none D2, this one will be none D1, this one will be both. Come from none D2 and come from none D2 and both if necessary, right? Similarly, yeah, to maximize use, we want all the values not divisible by D1 come from D2, And if that is possible, right, if that is possible, we can continue, check if the remaining availables are able to supply unique count 2. Similarly, we can handle all the values not divisible by d2 first and see if the remaining availables are able to supply unique count 1. Right, so these are the two things. Then we can build binary search on top of this, right? The max value that can be the high, right? The max high is a double of unique count 1 plus unique count 2, which happens, right, when d1 equals d2 equals 2. And at each time, at each step, we check if going with d1 first or d2 first works. As long as one of them works, we can shrink. If neither works, right, we increase, we expand. At the end of the day, I'll say, I mean, all of these, this one do on the outside, that's log n. And this is log this time, this plus this. Everything inside is all 1. So it's log C1 plus C2. That's the solution. All right, let's take a look. What happened? Oh, something is wrong. Something is very wrong. I think the web page is not responding. There we go. Now it is responding. LCM and binary search. One-liner. Oh my god. And you can do a formula. Oh, a lot more to learn. A lot more to learn. Okay. Oh, this is just a cheeky one. That doesn't really matter. They use the key. That's okay. Three criteria. Oh, that makes sense, right? So these are total capacity for 1 is the total capacity for 2, and there's total capacity for both. Oh my god. Wow. Magnificent. Max element in an array by adding the number of holes. trying to understand. I have something similar. What is this count? What is get max? The max elements in that array by adding the number of holes to the number of elements. So we have a D1, we have a D2, and count. What does this count? Is the total we want, or this is the max that we can get by doing this plus I know what this is. This is the number of times, right? Number of holes to the number of elements. So we have that much element. And then we need to add so we need that many numbers, right? So we divide by this. This will give me, yeah, all the like breakpoints. And then the last one. Yeah, I have this formula myself. Count plus this. I think I know what you're talking about. Okay, yeah, this is correct. This is the maximum available for this, and just to get a maximum available for both, we have two arrays. Yes, we need to insert a total of this. Multiples of this and this can be inserted into the other array. That is correct. Except for more, so we just cannot do this. Wow, this is smart. Yeah, I was actually know this one. Okay, so let's submit those two solutions. Much cleaner, right? Much cleaner than this. This is like gobble gobble. So many junk. So much junk. Alright, the first one is a better binary search. Oh, it's back up. Alright, so the total capacity for D1 is going to be... Oh, wait, hold on. I have to calculate mid first. Okay, the capacity for D1 has to be mid minus mid divided by divisor 1. The capacity for D2 is mid minus mid divided by divisor 2. Right? That's the total capacity. and capacity for D1, D2 for both is mid minus mid divided by LCM. So we say if capacity D1 is larger or equal to 1, or no, and capacity D2 larger or equal to unique count this, and capacity both is larger or equal to unique 1 plus unique 2, then we say high equals to mid, otherwise low equals to mid plus 1. Now I return low. Okay, let's see if this one is right. This is correct. Okay, now we have one more formula. Yeah, why would you, I don't know. The formula basically is similar idea, right? Solution 3. Find the max value if we only consider D1 and C1. Max value if we only consider D2 and C2. Max value if we consider both D1 and D2, C1 and C2. Take the max. No. Yeah, take the max among the 3. Def get max. Give me a D, give me a C, right? Or return an integer. The max value if we want to this smallest max value if we want to take C number of values not divisible by D. So what would you do? So basically we want a C count, right? And we want that many, and then there will be things interspersed, the multiples, right? How many? Because we will have basically from something something pa something something pa something something like this, right? So these add up to D. These add up to C, right? These add up to C. So what we want to do is to find the first C value, right? The first C value, how many are this, right? Among the first C value, how many are this? And then, yeah, because these are the C's. Yeah, hold on. I was able to figure this out yesterday. Now I'm kind of confused. Yeah, what's the max value for 1? That's not how I imagined. What was the one I used yesterday? Yeah, look at this. We need to have a unique count. Handle unique count 1 is C1 and D1 minus 1. Yeah, unique count 1. We want to have that many numbers. That's unique. I don't know. I wasn't able to get this. Like, I was able to get this yesterday, but now it didn't work for me anymore. Look, I have the formula here. Right? I have the formula here. But come on. What are we trying to do? We say we have the unique count, right? So we need to have that many. And we want to know how many are that we cannot do, right? Say we have unique count is 100. Oh, yes. Now I got it. That's the unique count, okay? So unique count, we divide it by this, so we know how many that we need. So it will be the unique count, right? Unique count plus all of this, yes, and we'll have the remainder, right? So that will be quotient r, yes, div mod count d minus 1, right? So we return we need a count plus q, right? Plus q, and then plus, well, it's actually no, it's minus int r equal to 0. Okay, because if r equal to 0, this is the last one we have to not do. If r is not equal to 0, that would be the last one. So that would be this. Then we just return the maximum of actually I think we'll have to do it this way. Right, maximum of get max divisor 1 count 1 yeah, because it works. We can like do D1, we can do D2, right? And we can do both. And the reason we can do both is because when we do both, we just say they're not divisible by this, so it'll be everything, like everything that's available, right? And then it works because we can always like swap them. And then we say get max, say D1. No, it's not D1. That should be the LCM. Okay, LCM and unique 1 plus unique 2. What was wrong? Ah. I'm still trying to think why this one will work. The maximum, if we want to consider this, right? The maximum we want to consider this. And it's like best case scenario. And this will be considering we don't take any of those. And if one of them is biggest, right? And then we can just say we can always satisfy this. And we remove everything that both, yeah, so just among these. And because this cannot, like, whatever is available here is also available here, right? So if this one is bigger than this, then it'll always work. If this one's biggest, right, it'll always work. I can just take this, I can take this, yeah. If anyone is the biggest, yeah, I think this does work. Amazing, huh? Amazing. Okay, that will be it. We'll save the tough one for tomorrow.